Hello everyone. Until now we have seen linear beam type tubes. One of the linear beam type tube that we have seen is klystron tube. Now we are going to see another type of linear beam type tube, that is O type tube, that is known as helix traveling wave tubes, that is TWTs. Okay, there are several traveling wave tubes. We are going to see only helix one. So what is a traveling wave tube? A traveling wave tube is a specialized vacuum tube that is used in electronics to amplify radio frequency signals in microwave range. So the primary job of these TWTs is as an amplifier. Okay, so these are used in amplifiers. So these belong to a linear beam tubes, as I said, O-type tubes, such as klystron. Klystron were also linear beam type tubes or O-type tubes, and klystron were also used as an amplifier, but klystron were also used as an oscillator, although that was rarely the case. For most of the operation, klystrons are not used as a oscillator, but in klystrons, radio waves were amplified by absorbing the power from a electron beam as that beam passes down the tube. Okay, so there is something different in this TWT compared to klystron. We will see what is the similarity and what is the difference between TWT and a klystron. Okay, although there are various types of TWTs, two major categories are helix TWT and coupled cavity TWT. Okay, out of which we are going to focus only on helix TWT because others are out of scope of our syllabus. Okay, so we will not focus on this one. So what is helix TWT? In helix TWT, radio waves interact with the electron beam just like klystrons had an electron beam and microwave input was interacting with it. But in this one, our input, that is microwave input, will interact while traveling down the helix wire. Okay, so when electron beam is traveling along the tube, a microwave input will travel along the helix wire. We will see the structure. Helix wire is a structure of a coil that we will see later on. So this type of tube has a wide bandwidth, but its output is limited to only few hundred watts. Okay, so if you want a very large power, these TWTs are not preferred, but their bandwidth is quite good. Okay, so when you want a amplifier which should produce uh, amplification at a large bandwidth, then these TWTs can be used. The second type, which is we are not going to focus, is a coupled cavity TWT, in which instead of a coil or helical structure, we will use cavity resonators, and these cavity resonators will be coupled just like what we have seen in previously in the other microwave devices. Okay, these coupled cavity function as a narrow band power amplifiers. Okay, these are preferred in the power amplification rather than normal amplification. So let's not get into detail of coupled cavity because our focus is on helix TWT. So comparing the TWT with klystron, we have said that klystrons and TWTs are slightly similar and slightly different also. So what are the similarities? In case of TWT, microwave circuit is not resonant. This is important. And wave propagates with the same speed as electrons. Okay, so whatever the speed of a electron beam, with the same speed, let's say this is a V, then microwave input or microwave signal will also travel with velocity V. Okay, so same speed will be there. The initial of effect on the beam is small amount of velocity modulation. What is velocity modulation? That we have seen in the klystron. Same velocity modulation will happen because still we are having a microwave input as well as electron beam. Both are there as klystron as well as TWT. So velocity modulation will occur because of weak electric fields associated with the wave. Okay, whatever electric field that is generated by microwave input that will cause a velocity modulation in a electron beam. Just as in klystron, this velocity modulation later translates into current modulation. How? Because this electric field uh, accelerates or deaccelerates electrons, and that means their energies, kinetic energies will be changed, which will be transformed into the RF current. That energy is transformed into the current, and that is current modulation, causing amplification, because flow of electrons is nothing but a current. So that's why current modulation is achieved through this velocity modulation that we have seen in klystron. So same thing happens in the TWT also. The difference between these two is, now we are going to see differences between TWT and klystron. Now what is the difference? The interaction of electron beam and RF field in TWT is continuous over the entire length of a circuit. So if the length of a circuit or length of a tube is like this, over entire length this interaction will happen. That is in TWT. But in klystron, interaction occurs only at the gaps of a resonant cavities. So we have seen multi-cavity klystron. There were multiple cavity resonators. So these are not connected. These cavity resonators were not connected. They were separated from each other at a certain distance. So microwave input was given to only first cavity. For latter cavities, there was no connection between microwave input and other latter cavities. Microwave input was given only to buncher cavity. So interaction started here, and that is carried over to the next cavities. Okay, so interaction is not throughout the length of a tube in case of klystron. Next difference is the wave in TWT is propagating wave. Microwave input continuously travels along the tube because of helical structure. Okay, whereas in the klystron it is given only to the buncher cavity. Okay, so klystron wave does not propagate, whereas TWT wave propagates. Which wave? The microwave input signal. In the coupled cavity TWT, which is another type of TWT, coupling is there between the cavities. In klystron, consecutive cavities were not coupled by any means, they were independent. So in TWT, each cavity in the klystron, in klystron each cavity is independent, whereas in TWT coupling between the cavities exist. Okay, so that is another difference. So that is a similarity and difference between TWT and klystron. So let's look at the structure of TWT. If you see, there is similarity with the klystron, as well as there are slight modifications also. So let's look at the common parts. We have a electron beam emitting cathode. Okay, then there is an anode also, which will attract the electron beam. Now this electron beam will travel down the tube. You can see over here, this is your tube structure. So travel down the tube electron beam and collected at the collector, similar to the klystron. Okay, then there are two magnets, this one and this one. These magnets are used to focus the beam along the tube. Okay, similar to klystron. The difference is, instead of cavity, now we are having a helical coil, or called as a helix. Now at one end of this helix, input is given, this is our microwave input, and at the other end output is taken. So microwave input travel through the tube and comes out, whereas in klystron microwave input was given here, and energy of electron translated into current was taken out as a output in the klystron. So that is the difference. So here microwave input will remain present throughout the tube. Okay, so helix traveling wave tube, other parts are similar. These are external power supplies, or heat supply, power supply, beam supply. All these supply voltages are there, so let's not discuss that in detail. Helix traveling tube consists of electron beam and a slow wave structure. What is a slow wave structure? This helical coil is called as a slow wave structure. Why? We will see later on. The electron beam is focused by a constant magnetic field along the electron beam and a slow wave structure that is shown over here. Okay, this is termed as a O-type traveling wave tube because this is a linear beam tube. Electron beam travels along the axis of a tube, so linear beam tube. The slow wave structure is either helical type or folded backline. So the structure of this particular slow wave structure is a helical one, and there can be other types also. We will see those types one by one later on in short. So in order to understand the operation, let's see the operation of the TWT. The applied signal, this is the applied signal, propagates around the turns of the helix. This is a helical structure. Helical means like a coil. So this wave travels along the helix, that is turns of the helix, and produces an electric field. This traveling of microwave creates an electric field, which is small, but yes, it is there. Okay, at a center of a helix directed along the helix axis. So it is generating an electric field at a center of that helix, which is along the helix axis. This electric field propagates with a velocity that is very close to the velocity of light. Okay, so it is very high velocity multiplied by the ratio of helix pitch to the helix circumference. So if we denote helix pitch as a P and circumference as a CI, it's not a correct notation, but for example, then velocity of electric field is C, that is velocity of light, into pitch divided by circumference of the helix. That is the velocity of electric field. Velocity of electric field. C, that is velocity of light, pitch is a helix pitch, and circumference of a helix. What is helix pitch? We will see that during the slow wave structures. Okay, when the electrons enter the helix tube, that is here, an interaction starts taking place between the moving axial electric field. So electric field and electron beam starts interacting. On average, electrons transfer their energy to the wave on the helix. So what happens is that as the electrons are traveling, they transfer their energy to the electric field which is generated by the moving microwave signal or propagating microwave signal. So that energy translation will increase the power of the microwave signal or amplitude of a microwave signal. So this interaction causes a signal wave on the helix to become larger. So because energy of electrons is translated into electric field which is generated by microwave signal, the signal wave becomes larger. That means its amplitude become larger. The electrons entering the helix at zero field are not affected by the signal wave. Okay, so initially it is not affected. Those electrons entering the helix at the accelerating field, so as the electric field is generated, it will have two components. One will increase the velocity, another will decrease. Increasing is a accelerating electric field and decreasing velocity is a retarding electric field. Okay, so those at the retarding field are deaccelerated. That's quite obvious, similar to klystron velocity modulation. As the electrons travel further along the helix, they bunch at the collector end. Okay, so similar to that, klystron bunching process will also happen over here and they will be collected at the collector end. The bunching process shifts the phase of the signal by 90 degree or pi by 2. Okay, this bunching will shift the phase of a signal by 90 degree. Each electron in the bunch encounters a stronger retarding field. Microwave energy of electrons is delivered by electron bunch on the wave on the helix to the wave on the helix. So as we have said, that interaction between electron and electric field which translates energy of electron into the electric field will be affecting the amplitudes of a microwave signal. Okay, that is wave on the helix. Thus we are increasing amplitude means what? we are getting amplification. Thus we have achieved the amplification of signal at the output end. Okay, so electron beam, because they are translating the energy or transferring their energy to the electric field, that electric field is generated by microwave signal. So indirectly microwave signal is getting affected, and because of that its amplitude gets increased, and amplitude gets increased means amplification is achieved. Okay, so this type of mechanism can be used as an amplifier. The characteristic of this type of TWT are its frequency range is 3 gigahertz and above. Bandwidth is about 800 megahertz or 0.8 gigahertz. Efficiency is about 20 to 40%, which is a decent one. Output is up to 10 kilowatt average. Okay, power gain up to 60 dB. These are just the statistics which are observed while using this type of TWT in a microwave amplifiers. So this is just a statistical data. So one thing that we have discussed is a helical coil, which is called as a slow wave structure. Now why this is called as a slow wave structure? Okay, so what is a slow wave structure? Helical coil is not the only one which is considered as a slow wave structure. Slow wave structure is a very broader phenomena. These are special types of circuits that are used in the microwave tubes to reduce the wave velocity in certain direction so that electron beam and the signal can interact. So why these are called as slow wave? These structures are used to reduce velocity. So velocity is reduced because of this structure. So if a particular, for example, if a particular person, if it is traveling in a straight line, then it can travel or it can run at a faster speed. But a same person, if it has to travel through a different rather than straight line, if it has to travel or run through a different path, like a zigzag path or circular path or helical path, then its speed will be reduced or its velocity will be reduced. Same concept is applied over here. If a microwave, which is usually having very high velocity, if we want that microwave to interact with electron beam which is having a low velocity, then we have to reduce the velocity of a microwave. So how to reduce the velocity of a microwave? Using this slow wave structure. And because it is reducing the velocity of a microwave, it is called as a slow wave, slowing down the speed of a wave, that is slow wave. As the operating frequency is increased, why then these structures are used? We can use resonant cavities also. In resonant cavities, only at a resonant frequencies interaction will happen. But in that case, inductance and capacitance of the resonant circuit must be decreased in order to maintain the resonant at the operating frequency. This is because they are not a distributed elements, they are active elements and their behavior changes as the frequency increases. So that is one of the reason resonant circuits are not usually used. Now the gain bandwidth product is, we know that it is a constant and it is limited by this resonant circuit. So if we change the inductance and capacitance, our gain bandwidth product will get affected. So because of that, large output power is not possible in case of using a resonator in order to reduce the speed of a wave. So resonators are replaced by these different structures. Several non-resonant circuits, or these are called as now slow wave structures, are designed for this reason to produce a large gain over a wide bandwidth. So why we are not using resonator? Because inductors and capacitors are changing their values at resonant frequencies. So to maintain a resonance, we have to change the values of inductors and capacitors from time to time. So we are avoiding them. So non-resonant structures, now which will be called as a slow wave structures, will be utilized, which can provide a large gain over a wide bandwidth. We don't have to change anything. At a wider bandwidth, we can get a larger gain. Okay, so the commonly used slow wave structure is helical coil, just we have seen, with a concentric conducting cylinder. There are several other types as well. We will see that one by one. These are 5 types of slow wave structure that are shown. This is helical one that we have already seen. This is folded backline. That means wave will travel along this path. This is zigzag line. This is interdigital line. Wave will travel like this. Okay, and fourth one is a waveguide, corrugated waveguide. That means inside a waveguide we are creating a corrugation, that is different types of slot, so wave can travel between these slots and its speed will be reduced. Okay, so out of which this one is most popular, which is used inside a helical TWT or TWT, that's why it is called as a helical TWT. So one thing that we have seen, what is a slow wave structure. Now next thing, what is a pitch of a slow wave structure. So what is a pitch of a slow wave structure? Now pitch of a slow wave structure is denoted here by P, the distance between two consecutive turns of a coil, that is called as a pitch. Okay, it is denoted here also. Okay, this is the axis of a helix. This is axis of a helix. Now distance between two consecutive turns is a pitch. Now it can be shown that ratio of phase velocity. How to calculate phase velocity along the pitch to the phase velocity along the coil. Velocity of a wave along the pitch to the velocity of a wave along the coil. Along the pitch means in the forward direction, along the coil means in this particular helical structure. Okay, that can be given by phase velocity upon speed of light. Okay, it is given as p upon square root of p square plus pi d square, that is equal to sin psi. How this is calculated? Now the total diameter of this diameter of the helix is said to be d. Okay, diameter of helix is said to be d. Now pi into d is the phase velocity in the upward direction. Okay, or this is the total distance. Total distance is given as pi into d. Okay, and this distance is given as pitch, p. So psi is a pitch angle. Okay, pitch angle is given by normal to the direction of propagation of a electron beam and the pitch. So this is angle is psi angle, that is called as a pitch angle, and sin psi is this value. Okay, so p upon p square plus pi d square is equal to sin psi. Okay, so if we take a sine of this pitch angle, we will get this answer. So this is nothing but phase velocity along the pitch, that is Vp, and phase velocity along the coil, that is considered to be as a speed of light. Okay, so since speed of light is larger, phase velocity is smaller, this value will become lesser than 1, and that is slowing down now the wave. Okay, where c is a speed of light in free space, p is a helix pitch, d is the diameter of the helix, and psi is a pitch angle. The phase velocity in the axial direction is now expressed as, considering the permittivity and relativity of the medium. Free space we can assume mu 0 and epsilon 0, but we are not having free space, that there can be a different medium also. So considering those, the equation will become like this one. Okay, only additional part is these two, otherwise phase velocity is same. For very small pitch angle, that means if psi is very small, then what will happen? The phase velocity on the coil in free space is approximately represented by Pc upon pi d. P is a pitch, C is a velocity of light, and pi d is a diameter into a particular constant, which is actual distance. Okay, that is given by omega upon beta. Okay, this is for only small pitch angle. If pitch angle is substantial, small pitch angle means what? Turns are very sharp, and large pitch angle means what? Turns are very slow. This is a large pitch angle. Okay, so for large pitch angle you can follow this. For small pitch angle, phase velocity is given by this. Okay, so now next thing, in order to understand how the amplification happens, first thing we have to understand is a working of this helical slow wave structure, which impacts on the phase velocity. Now figure shows a omega beta diagram. Omega is angular frequency and beta is a phase constant, which is called as a Brillouin diagram for a helical slow wave structure. This diagram is a plot of phase constant beta versus at angular frequency. Okay, so when wave is traveling at a speed of light, omega upon beta will be like this one, but when it is slowed down, this ratio will come down to the lower slope. The helix omega beta diagram is very useful in designing a helix slow wave structure. One thing that is important, what should be the pitch angle and what should be the value of pitch while designing a helical slow wave structure. For desired amplification of a microwave input, important parameter is, I am repeating now, for desired amplification of a input signal, the pitch angle and pitch both are important, and that is decided based on this Brillouin diagram, that is omega versus beta diagram. Once beta is found, that is phase constant, Vp can be computed from the equation of group velocity. Now, what is group velocity? It is simply the slope of this particular diagram. The group velocity of wave is merely slope of the curve as given by d omega by dw, or dou omega by dou w, dou beta. Okay, so that is group velocity. Once beta is known, that is phase constant is known, then you can find out group velocity, from which you can find out the values of pitch and pitch angle. Okay, so that is very important for a amplifier design. In order to circuit to be a slow wave structure, so can any circuit be a slow wave structure? There is condition, it must have a property of periodicity in the axial direction. That means it cannot be like that. First, the distance between two consecutive turns should be constant one. It should have certain period, so that there should be periodicity. This is not allowed. There should be certain periodicity in the axial direction. So this type of structure is not allowed for a slow wave structure. The phase velocity of some of the special harmonics in the axial direction obtained by the Fourier analysis of waveguide field may be smaller than the velocity of light. Now this understanding, under meaning of this statement, we will understand in the actual amplification process that we are going to discuss in the next video. So phase velocity is a harmonic in nature because of this periodicity. Periodicity provides the harmonic nature to the phase velocity, and if we draw a Fourier analysis of it, then we will see that there are some velocities which are greater than 0 and some are smaller than 0. So these are called as spatial harmonics, harmonics in the space dimension. Okay, so how that will affect the amplification process, that we will see in the next video. But this helical slow wave structure or translation back or forth through a distance of one pitch length results in the identical same structure again. So because of this helical periodicity, so the wave is continuously slowed down at a constant rate, and thus period of a helical structure is its pitch. So what is the period? The pitch between, or the distance between two consecutive turns. Okay, so that is important statement. The period of helical slow wave structure is its pitch. Okay, So this will decide how the amplification process will happen. The amplification process we will see in the next video. That's all for today. Thank you.